In 2004, Google released a paper introducing a programming paradigm called MapReduce to distribute the data processing to hundreds or thousands of machines. In MapReduce, users have to explicitly define the map and the reduce functions. Map. It takes key/value pair inputs, processes them, and outputs intermediate key/value pairs. Then, all values of the same key will be grouped and passed to the reduce tasks. Reduce. It receives intermediate values from map tasks. It then merges the intermediate values from the same key using the defined logic, for example, count sum. To ensure fault tolerance, for example, a worker dies during the process, MapReduce relies on disk to exchange intermediate data between data tasks. Based on Google's paper, Yahoo released the open-sourced implementation of MapReduce, which soon became the go-to solution for distributed data processing. It rose and dominated, but it wouldn't last long. The strict map and reduce paradigm limits the flexibility, and the disk-based data exchange might not be suitable for use cases like machine learning or interactive queries. UC Berkeley's AMPLab saw a problem that needed to be solved. Although cluster computing had a lot of potential, they observed that the MapReduce implementation might not be efficient. They created Apache Spark, a functional programming-based API to simplify multi-step applications, and developed a new engine for efficient in-memory data sharing across computation steps. Unlike MapReduce, Spark relies heavily on in-memory processing. The creator introduced the Resilient Distributed Dataset, RDD, abstraction to manage Spark's data in memory. No matter the abstraction you use, from dataset to data frame, they are compiled into RDDs behind the scenes. RDD represents an immutable partitioned collection of records that can be operated on in parallel. Data inside RDD is stored in memory for as long as possible. To operate efficiently, RDD has some information. List of partitions. An RDD is divided into partitions, Spark's parallelism units. Each partition is a logical data subset and can be processed independently with different executors. Computation function. A function determines how to compute the data for each partition. Dependencies. The RDD tracks its dependencies on other RDDs, which describe how it was created. Partitioner, optional. For key-value RDDs, a partitioner specifies how the data is partitioned, such as using a hash partitioner. Preferred locations, optional. This property lists the preferred locations for computing each partition, such as the data block locations in the HDFS. When you define the RDD, its data is unavailable or transformed immediately until an action triggers the execution. This approach allows Spark to determine the most efficient way to execute the transformations. Transformations, such as map or filter, define how the data should be transformed, but they don't execute until an action forces the computation. Because RDD is immutable, Spark creates a new RDD after applying the transformation. Actions are the commands that Spark runs to produce output or store data, thereby driving the actual execution of the transformations. Spark architecture. A Spark application consists of driver. This JVM process manages the entire Spark application, from handling user input to distributing tasks to the executors. Cluster manager. This component manages the cluster of machines running the Spark application. Spark can work with various cluster managers, including Yarn, Apache Mesos, or its standalone manager. Executors. These processes execute tasks the driver assigns and report their status and results. Each Spark application has its own set of executors. The Spark driver executors cluster differs from the cluster hosting your Spark application. To run a Spark application, there must be a cluster of machines or processes, if you're running Spark locally, that provides resources to Spark applications. The cluster manager manages this cluster and the machines that can host driver and executor processes, called workers. Thank you for staying until the end. If you enjoyed this piece, please give it a like or leave a comment. You can visit my newsletter at vutr.substack.com for deep dive data engineering articles. I publish weekly for over 18,000 data engineers.